I wanted to take a brief interlude this lab to go over the concept of likelihood. Since we're discussing AIC and BIC a little bit more in depth this week, and these are both based on the idea of likelihood, I thought this would be a good time to go over this. It will also be an important building block for when we talk about Bayesian estimation in a few weeks. So what is likelihood? The technical definition of likelihood is that it's the probability of observed data, which is denoted with capital D, given particular parameter values, which are denoted with theta. And this could be one parameter or many parameters. Theta can often represent a whole space of parameters. And so likelihood is often written in this way, P D vertical bar theta, so that's probability of D given theta. Since our observed data are fixed, we already collected our data and we know what our collected data looks like. We have our sample, and we're trying to estimate our parameters. The idea of maximum likelihood is that we're trying to find the parameter values that maximize this probability. And we can sort of visualize this with a likelihood distribution function. So here what we're saying is we have a set of data, and we want to know what the probability that this exact set of data would have been produced by some parameter, and that's what's on the x-axis. So here we see that, we have, in this case, we're envisioning this as being a one parameter model, and that when that one parameter is 200, that's when we would have been most likely, that's the parameter value that would have been most likely to have produced this data. But the chances of this exact parameter producing this exact data are still fairly small. It's only less than 1%. But that's still the parameter that has the highest likelihood. If we move away from 200, we see that the probability of this exact data being produced by, say 0 or 400 is even smaller. It's very, very small. It's less than 0.5%. So the idea behind maximum likelihood is we're trying to find the likelihood that's at the highest point. We're essentially trying to climb this hill and find the parameter value that would maximize the, the, the likelihood of this exact data set. In complex models based on lots of data, likelihoods get extremely close to zero. They get really, really small. And when you take the log of a number between 0 and 1, that results in a negative number. As numbers approach 0, their logs approach negative infinity. So this is why we take the log likelihood. We know that the log of any likelihood, which remember it's a probability, so it's between 0 and 1. So the log of any number between 0 and 1 is going to be some negative number. And for really, 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 really small likelihoods, which we're often going to be dealing with, these are going to, taking the log gives us a really, really big negative number. And this serves two purposes. First, computers have a really hard time with really small decimals. So this is really just a computational practical issue because computers don't have enough memory to really handle numbers that have lots and lots and lots of zeros before the decimal, after the decimal, and they can't deal with these numbers with any real precision after a certain point. So by taking the log, we instead deal with very large negative numbers, and computers are much better at dealing with these with precision. The second reason is that it helps the computer do the math. So for example, taking the log of a product is equal to the sum of the log of both of its elements. This is the sum rule in dealing with logarithms. And this comes up a lot where you're multiplying lots of small probabilities. Instead of doing that, now what we can do is we can add the logs of these probabilities together. And so instead of multiplying really, really small decimals, we're adding together very large negative numbers, which just works out way better for our computers. Another important concept is the saturated model. You can think of the saturated model as a model with perfect fit, or a model with 0 degrees of freedom. And that means that there's one parameter for every observation. In HLM, a saturated model has a likelihood of 0. This is essentially a model where we're saying the data is the model. Deviance is a way of thinking of likelihood in terms of how far your model, which has degrees of freedom, deviates from the saturated model, the model with perfect fit. So comparing a model with degrees of freedom greater than 0, which is, again, a model that has fewer parameters than data points, so that means that the parameters can have some freedom in how we estimate them. They can have some variability, to a model with 0 degrees of freedom, which is a model with perfect fit with one parameter for every data point. We can see how much a model deviates from perfect fit. Deviance is computed as -2 times log likelihood. And smaller deviance means a model deviates less from the saturated model. Or it also means that its likelihood is greater. So how do we make use of likelihood in comparing models? Well, when we compare nested models, what we're doing is we're comparing special cases of the same model, really. So let's say you have a model with 3 predictors, and you fix one of those predictor parameters to 0. Now you have the same model, except you fixed one of the parameter values, and you can compare what happens when you fix one of those parameter values to 0. That's what we're doing when we compare nested models. We're treating the reduced model as a special case of the full model, and so we can directly compare how well they perform. When models have different parameter structures, we can't treat them as special cases of one another, but we can compare their likelihoods or their deviances. The problem is we still need to avoid overfitting, and that's because the more parameters you include, the more you're going to improve the likelihood, the closer you're going to get to the saturated model. But the more likely you are also to just have a parameter that is capturing some random noise in the sample and not something that you're interested in, not something that's actually a real feature of the population, just something that was part of the sampling noise in your sampling procedure. Another way to think of the saturated model is that it's the most overfit model possible. It assumes every data point is perfectly deterministic. And this would be reasonable only if you had the entire population. If you did have data on the entire population, then the saturated model would be somewhat sensible because you're saying that each data point is deterministic. But this isn't, when we're sampling, this isn't a reasonable assumption. When we're sampling, we're saying each data point is not perfectly deterministic. We know that there's sampling error. So what we want is a model that has a likelihood as close to the saturated model as possible without including so many parameters that one or more are probably just capturing random noise. This is where information criteria methods come in. So information criteria penalize log likelihood for each additional parameter included. That way, what you're saying is essentially the benefit of adding the extra parameter to the likelihood has to make up for the penalty that you're introducing in the information criteria. The two most common information criteria are AIC and BIC. And BIC is Bayesian information criteria, but this is a bit of a misnomer. It's not really a Bayesian method. So the way these are computed is based on the deviance, which remember is -2 times the log likelihood. So where k is the number of parameters and n is the sample size, AIC is the deviance plus 2k. So it's the deviance, which remember we're trying to reduce the deviance, and then it increases it by 2 times the number of parameters. So again, we're penalizing the deviance for having extra parameters. And BIC is a little bit more complicated. It's the deviance plus the number of parameters times the log of the sample size. So it does take the sample size into account here. The main difference between them is that BIC will sometimes be a little bit more conservative in terms of adding extra parameters, but they're often going to agree with one another. And again, the idea is we want to lower these, because remember, these are based on deviance, and lower deviance means better fit. So lower values of AIC and BIC mean better model fit, and we can use these to compare models even if they're not nested with one another. The downside is these information criteria don't have any absolute meaning. They're kind of just arbitrary numbers. What they're really doing is comparing different models to the saturated model, and then you can sort of transitively compare both of those models that are compared to the same saturated model to each other. Because remember, if they're both being compared to the same saturated model, that just means they're being compared based on the same data, or the same outcome variable in particular that has the same data. So we've already seen how to obtain a likelihood ratio test and how we can get AIC and BIC using the little a ANOVA function. And we're going to look at this a little bit more in the next set of slides. And the same procedure here applies to non-nested models. The only difference is when we have nested models, we can interpret the likelihood ratio test part. When we don't have nested models, we just ignore that. And we only look at the AIC and BIC. In all these cases, we still need to use full maximum likelihood to compare models with different fixed effects. But once again, the only real other difference is that When models are nested, we can do an actual likelihood ratio test. When they're not, we can only compare these information and criteria metrics.